quiz and practical isn't until a week from, like a week and a half. It's not next week, it's like. Are there any questions? Questions before we get started? Yeah, the quiz and practical is the study guide current. The study guide is current. I've updated it.
That's what the study guide said. There was like a lot.
Let me go check. I definitely updated the practical.
Okay.
I'm gonna check the quiz.
Yeah, the practical looked updated, but the first one, the study guide, the quiz were
Double check. Any other questions before we get started? Oh, Jess, you have an announcement?
yeah.
Hey everybody, if you can listen up to Jess, please.
Next Tuesday is the last Pre-Nursing Society meeting of the semester, and we're having a TEAS and HESI panel. So if you guys don't know, to get into nursing school, you have to take an entrance exam. There's 2 different ones, and you take whichever depending on what school you want to apply to. So the private schools tend to prefer the HESI, and the state schools tend to prefer the TEAS. So we're having people who have taken both tests and passed and done well sit on a panel so you guys can learn about the types of questions and ask them questions. And also on Thursday, oh, that's tomorrow. Tomorrow, there is a blood drive that's being sponsored by the Pre-Nursing Society. It's right here on campus. So if you feel like you want to help save lives, giving blood is always good. I didn't know this, but I learned it recently. The blood bank has to replenish their supplies. They can't keep blood forever. It only lasts for so long. So even if they have plenty of blood, if that blood reaches an expiration date, they have to throw it all out. So donations.
Do you know where?
I believe the blood drive is in parking lot number 8. So like the main parking lot, I think by the, by the theater.
Theater? Okay.
Yeah. And the blood drive's from 10 to 2, and the Pre-Nursing Society meeting is in SC 601, which is this room right next to us.
What time?
5 to 6.
Cool. You ready? What did I draw here? That's an erythrocyte. You know it because it's got its nice round shape and it's biconcave, so it's a little more transparent in the middle. What kind of white blood cell has 3 lobes and lightly stained granules? The neutrophil. What kind of blood cell has generally a bilobe nucleus and they're dark but not too dark. They're kind of pinkish red. Eosinophils. Neutrophils, can anyone tell me something about neutrophils? What's interesting about them? They're the most abundant white blood cell, most abundant white blood cell, leukocyte. The what? They're phagocytic. What does that mean? They eat things. They leave bacteria, they leave debris. Eosinophils, what are their granules good for? Fighting parasites. They kill parasites. That's one important function of eosinophils.
I was gonna ask for the erythrocyte, like on the when you look at it for histology, how can you tell where the divot is? Because I was looking at it through the microscope and it looked very like it looked like just a red circle.
I mean, hopefully when you're looking at erythrocytes, how can you tell where the divot is? It's like if you're looking at it straight on, here it's nice and round and then it's lighter in the middle. So this is where it's concave. And then here, I've tried drawing a cell that has tons of granules that it masks the nucleus. That's a basophil. What do basophils do? What's all that granule good for? Creating inflammation.
Oh, histamines.
Yeah, they release things like histamines, which create inflammation. Things like heparin, which prevents clotting, prevents coagulation, helps mediate immune response. Those are the ones we've talked about so far. And we've talked about some types of anemia, which I'll review in a minute.
Is there any, like, the food effective for those cells or not?
Are there
The food, like whatever we are eating, is
foods that can,
affect.
is there a food that can help with any specific cell? I don't know if it can help with a specific cell. I mean,
No, like, is it genetic or?
to produce these cells?
Yeah.
Yes. We have the.
Okay, okay.
I mean, we all normally make these cells. I'm sure if there was a genetic condition, you could stop making these cells. There could also be acquired conditions where you stop producing these cells. So. Right. Okay. We talked about eosinophils, basophils, monocytes. Monocytes are pretty large. They don't have granules, and their nucleus is kind of kidney-shaped. No granules, large kidney-shaped nucleus. Monocytes, they'll eventually develop into macrophages. So that's like what they'll eventually differentiate into. What the name implies is that they are large cells that eat things, macrophages. So macrophages are like neutrophils. They both eat things. They're both phagocytic. One major difference, at least appearance-wise, they don't have granules. They're agranular. Sorry?
But they still stain dark.
The nucleus stains dark. Whoops. Which way? The nucleus is dark, but the cytoplasm is pretty clear. It's not even perfectly clear, but it doesn't happen. Let me go back to neutrophil. In a neutrophil, you can see regular dots all around. And you have a multi-lobe nucleus with a monocyte, kidney-shaped nucleus. Very, very big things.
No, I was just gonna say you can't really see the
The outline?
Yeah.
Oh. Yeah, there should be better contrast on this picture. The outline's like that. It's a circle.
Is it easy to tell the difference? I guess the bilobes, the eosinophils, they have the pink granules. That's fine. Okay.
Yeah, the eosinophils have pink granules and they're bilobed. I know that looks kind of similar to this kidney-shaped nucleus, but there's no granules. So. All right, last white blood cell that we're going over, leukocyte, is a lymphocyte. Lymphocytes, we'll talk about the lymphatic system. You've probably heard of that term before. Might not know what it is exactly. We have lots of lymph organs, like lymph nodes. Lymphocytes are found in high mountain places like that, but they're also found in your blood. They are pretty basic to identify. They're nice and round, and their nucleus is also big and round. It takes up pretty much the whole thing. There are no granules, just one large nucleus. There are many different types of lymphocytes, and you'll learn about them when you get to physiology, things like helper T cells and cytotoxic T cells and other types of lymphocytes, natural killer, cool names. They don't have granules, nice large round nucleus, but they can do tons of different things. For example, they're the ones, one type of them are the ones that produce antibodies. So when you get infected, the first time you get these lymphocytes to make these antibodies, so then when you get infected the second or third or fourth time, you can fight it off like it's no problem. Or when you get vaccinated, you produce antibodies so that you have natural immunity or artificial immunity against that thing. We do have slides somewhere in lab. I don't think we had it yesterday, but we have slides of different types of leukemia. This example is where you have lymphocytic leukemia, where you have just a high amount of lymphocytes. And I know that sounds good to have a lot of white blood cells, but these are abnormal, and so to have lots of abnormal cells, that's not what we want. Yes?
Are these cells that would be found in like the immune system?
Yeah. I mean,
Are there any other like?
so when you say what are these cells found in the immune system is lots of things. It's
Okay.
your blood, it's organs like your spleen, your tonsils, your lymph nodes. We're going to go over that coming up. But yeah, it's found in all those organs. So we talked about. Oh, let me back up. Actually, we talked about the spleen. In the spleen, what happens?
It takes out the destroyed.
It takes out red blood cells. Erythrocytes are destroyed in the spleen. We need something to do the destroying. Which one of these cells could destroy erythrocytes? Yeah, these are found in high amounts in the spleen. We'll see. Lymph nodes, places like your stomach and intestines especially, you find large amounts of macrophages and lymphocytes to help fight off infection. We'll go over all this when we get to the lymphatic system. At least for now, I want you to be able to identify what these are. All right. We talked about erythrocytes. These are all leukocytes. This is not a leukocyte or an erythrocyte. It's its own thing, really big. This is a really big cell called a megakaryocyte. And megakaryocytes are neat because they're only in the red bone marrow. So shown here is red bone marrow. And you can see where the green lines are pointing. Those are two examples of megakaryocytes. Very, very large compared to the rest of the cells. These are the ones that shed membrane. They're shedding endoplasmic reticulum to produce platelets. And platelets are just fragments of megakaryocytes. So you can see platelets under the microscope. Let me go back real quick. Let's see in there. Maybe. Come on. There's one. There's a platelet. So when you see purple specks on a blood smear, they're likely platelets, not just random debris. The rest of these cells here, what are these? What are they doing? I mean, we're in the red bone marrow, so what's happening? I heard red blood cell production.
The immature version.
Immature versions of red blood cells, is that the only thing happening? What else is made in the red bone marrow? Besides erythrocytes.
White blood cells.
All blood cells are made here. So all these cells, these are stem cells.
Oh, reticulocytes.
Reticulocytes are the immature red blood cells, yeah.
Are you platelets only found in the bone marrow?
Pardon, say it again?
Platelets only found in the
Are platelets only found in the bone marrow? Platelets are made in the bone marrow, they're released into the bloodstream. It's released into the bloodstream. Do you want me to repeat what I said? So I said that if we're looking at red bone marrow, which is found in the ends of long bones, epiphyses, some of the cells are these megakaryocytes which split off platelets and platelets enter the bloodstream. Most of these cells are stem cells of some kind. and these stem cells differentiate into either erythrocytes or some kind of leukocyte. All blood cells, all things from the blood, no, all blood cells are made in the red bone marrow. That's more accurate. All blood cells are made in the red bone marrow.
You said that the darker ones were those the stem cells, and then what
So these, like this really large cell, and this really large cell, and this one, those are the ones I see. Those are all megakaryocytes. Everything else is some kind of blood cell in development. Could be red, could be white. Can't tell it's right. So platelets are just fragments. They're really small. They're smaller than even erythrocytes. So look for really small purple stained things when you look for platelets.
And they are helping for circulated blood.
So why do we have platelets? They're these little fragments. They're not going to be carrying anything. They're not carrying oxygen or nutrients. They're not fighting off infection. What platelets do is that they circulate around, and if you have a damaged blood vessel, the platelets get activated and stick to that area.
Oh.
It's like if you have a leak and you just need something temporary to stop the leak before you get something more permanent. It's like sticking your thumb or a piece of gum in a hole. That's what these platelets are doing. They're the beginning of the coagulation process. It's a 3-ish step process. This is the first step. Putting what's called a platelet plug. You'll learn more steps when you get to physiology. Yeah?
So that would be important for surgery?
Would this be important for surgery? If you're cutting into a blood vessel, for sure. Because in some cases you might not want clotting to happen, because you might need to fix something inside of a blood vessel. So you might need to give an anticoagulant. So normally platelets are inactive, but they can sense damage, so to speak. When you have a damaged blood vessel wall, collagen gets exposed. You know the collagen, right? Collagen activates platelets, and platelets become sticky. So in areas where there's damage, that's when it starts sticking. It doesn't just stick to any part of the wall. That would be really bad because then you'd get clots all the time. You only want it to stick in areas of damage, and it only knows where areas of damage are when there's exposed collagen. Again, here's a platelet, really small.
Can you say again that the platelets were a 3-step process?
Yeah, what I said was platelets are needed for the beginning of the coagulation process. A platelet plug forms, and then the actual clot, it's called fibrin, forms, and then once you get the healing, then the clot goes away. So this is just a temporary fix. Not very strong, but it's there to stop the disease. Yeah. Right, okay, so if you remember my weird analogies, we've got delivery cells like red blood cells, that's delivering oxygen and nutrients and getting rid of wastes. We've got our emergency team, like white blood cells eating things up, like phagocytosis or secreting granules. And we've got things patching things up, like our platelets, plugging up holes and making sure we don't bleed out. All right, take a moment. These are the questions. hand a few more times. Hands on 3. 1, 2, 3. On 3, say the letter. 1, 2, 3. B. B. Yeah. What type of cell is this? Eosinophil. Eosinophils. This one. They fight parasitic infections. Another question?
Okay. I just wanted to check before I started.
It's really be focused on the ones that are related to eye and ear and vestibular sense.
Okay.
Raise your hand a few more times. Hands on 3. 1, 2, 3. On 3, say letter. 1, 2, 3.
A.
Yeah. Lymphocytes do not have granules. They fight off infections in different ways, usually with receptors or release of antibodies, but really not later. Cool. All right. That's it for blood. So I gave you, or Isabel passed out 2 packets. One says the actual title of the PowerPoint on it, Chapter 22 of the Heart. The other is a continuation of it, so it's like Part 2. Think of that as Part 2. Is there another sheet of paper? A blank sheet of paper that you can turn in? Even if it's a half sheet, if you could share with someone next to you if they don't have one, get a half sheet of paper. On that half sheet of paper, what I'd like you to do, write your name first. Name at the top. And then just draw like a body outline of a person in anatomical position. Doesn't have to be great. Just like, here's the head, neck, shoulders, and back. Something, I can't even fit it on here. You'll hopefully have more space. But something like this. And then they're like down. Draw a body outline. One important thing that we're going to learn is not only how the heart works and cells of the heart, so histology will be important. We're going to go over cardiac histology again. We're going to learn about how blood passes through the heart and how it goes through the whole body. So heart, blood vessels, it's all connected, obviously. So we're going to learn about all those different things, the path of blood through the heart and through the whole body, and the anatomy, the gross anatomy and histology of the heart. So the first thing I'd like you to do, don't confer with anyone. I want this to be all your own. You're not graded on your accuracy here. I just want to see what it is you think currently, and hopefully if you do have an incorrect assumption, then that'll change. I want you to, on your person, draw a heart. And then preferably in a different color. If you don't, no big deal, but just some way to indicate. I want you to show me the path that blood takes, how you think it works, the path that blood takes from the heart to the right toe. I said the right toe. So again, without talking to anybody, tell me on looking at this person which one is the right toe, and then back to the heart. How does blood circulate? Draw a path. So there should be a start, and there should be a finish somewhere. But I want you to show me on this body, how will we get to that toe and back? Again, if it's incorrect, it's not a big deal. I just want to see what you think. All I'm looking for is an outline of a body and a line showing where blood is flowing. To the right toe.
And then come back to
From the heart to the right toe, back to the heart. Right big toe, I guess I should say. About another 30 seconds. Again, it doesn't have to be artistically awesome, just show me where you think it goes. Cool. Please pass it that way. Just curious to see what you all think. Yeah. It's fine. We'll return. We'll get back to this. I'm not going to answer it right now. We'll find out. What? I mean, there's an anastomosis if you have like blood area. That maybe. Okay. Attention, please. So, we're talking about the cardiovascular system still. We just finished talking about blood, the stuff that's flowing around in your blood vessels. So, how do we get that blood to flow around? We need our heart. We can't just rely on gravity alone to move blood around or diffusion. We need a heart to pump and circulate blood. Our heart is divided into two parts. It's actually even 4 parts, but we'll go over these 2 for now. Remember that word septum, like septum pellucidum? It means wall. It's a dividing thing. Just like we have a septum of our nose, we have a septum of our heart. It's the thing that divides our heart into the right side and the left side. This is the right side because we're looking at it. This is the left side. So the septum divides the heart into right and left halves. We have blood vessels that distribute blood away from the heart and to the heart. We'll get to more specifics about these later, but you should know these terms for now. A vein, the definition of a vein is a vessel that carries blood back to the heart. So here is a vein carrying blood from somewhere else in the body back to the heart. That's a vein. This is also a vein. This is carrying blood back to the heart from the lungs. But this is oxygenated blood, this is deoxygenated blood. So when we talk about veins, it's not about oxygenation. It's about where it's delivering the blood to. A vein delivers blood to the heart. If it's coming from the lungs, it's going to be oxygenated. If it's coming from the body, it's going to be deoxygenated. An artery carries blood away from the heart. So here is oxygenated blood going away from the heart. That's an artery. Here's deoxygenated blood going away from the heart. That's also an artery. Can anyone see the benefit of having a septum? We don't mix the oxygenated and deoxygenated blood. That's the evolutionary advantage of having a septum. The smallest blood vessels, the most branched blood vessels, the ones with highest surface area, those are capillaries. And capillaries help with exchange. By being thinner walled, that allows for high exchange, high rate of diffusion. So we have capillaries throughout our entire body, including the lungs, so that we can get oxygen and get rid of carbon dioxide. And we also, of course, have blood in those blood vessels carrying, well, I erased it, the cells that we have and plasma, the solution of our blood. Cool? Okay. More about the heart. By having that septum, that means we have two different circuits, two different full circles, full loops of where blood is delivered. We have a pulmonary circuit and a systemic circuit. Pulmonary, that word means lungs. Systemic to the rest of the body. Systemic means whole body. So our pulmonary circuit is relating to our right side of the heart. From the right side, we deliver deoxygenated blood to the lungs. Our lungs oxygenate the blood and then bring it back to the heart. That's the pulmonary circuit. From the right side of the heart to the lungs to the left side of the heart. You're reoxygenating blood. The systemic circuit exits the heart, goes throughout the body. We deliver oxygen and nutrients to the rest of the body, and then we return the now deoxygenated, nutrient-depleted blood back to the right side of the heart. Pulmonary circuit, systemic circuit. Forward. Two loops, and by having a septum that allows for these two circuits. All right, here's the path. Here's the general path of the pulmonary circuit. From the, oh, right, I have to introduce these strips. So we have the septum that divides left half and right half. We also have valves, and we'll go over the valve names later. We also have valves. I should have gone the other way. We have valves that separate each half again. So on the right side, we have. Can you close the door, please? Plane, what is that? A seagull? Some light now. Alright, this will do. Alright, from the pulmonary circuit. From the right atrium, this is called the right atrium. These top two chambers are called atria. Atria is plural. This is the right atrium, this is the left atrium. So from the right atrium, blood is pumped out. Sorry, I'm getting ahead of myself. Right atrium, blood is pumped down. Right atrium to the right ventricle. Right atrium to the right ventricle. So these two are atria, these two are ventricles. right atrium, left atrium, right ventricle, left ventricle. The order is blood goes from the right atrium to the right ventricle. The right ventricle then pumps blood. You have to imagine this in 3 dimensions. The right ventricle pumps blood out of the heart through the pulmonary trunk. I'm not happy with my drawing. Let me draw it. All right. Okay. Here's the right atrium, to the right ventricle. From the right ventricle, it goes out the pulmonary trunk. So this thing is the pulmonary. If you hear the word trunk when we're talking about blood vessels, it means it's a short, wide blood vessel. If you hear the word trunk referring to blood vessels, it's a short and wide blood vessel. There are other trunks that we'll go over. It is still an artery. This pulmonary trunk is an artery because it's exiting the heart. But it's called a trunk because it's short and wide. The pulmonary trunk splits. It'll branch. It'll branch to the left and it'll branch to the right. These are the pulmonary arteries. So this would be the right pulmonary artery. This would be the left pulmonary artery. Sorry, vein. No, artery. Artery. It's going away from the heart, it's an artery. There we go. We have 2 lungs, one on either side. So these arteries will branch. I'm going to signify branching like this, like this waffles thing. Sneeze. All right, so these are pulmonary capillaries. On either side, and you find pulmonary capillaries surrounding the lungs. So you have capillaries on either side. This is where gas exchange happens. The capillaries here in the lungs are needed for gas exchange. Not so much for nutrient exchange, because they're actually a different set of capillaries. This is for gas exchange, pulmonary capillaries. Returning back to the heart, to the left atrium. So here's the left atrium. These capillaries will branch back into larger blood vessels. There's actually 2 sets. There are 4 pulmonary, I should use red. There are 4 pulmonary veins. These are pulmonary veins. 2 from either side. Adela, do you have a question?
Yeah. For the gas exchange, is it oxygen and carbon dioxide? Are those the gases?
Yeah, what are the gases being exchanged? It's oxygen is coming from the lungs into the blood. Carbon dioxide is leaving the blood out to the lungs, and you breathe that out. And we end up in the left atrium. That is a full circuit, starting from the heart, ending in the heart. Yes.
So as far as the function of the pulmonary circuit, it's just taking unoxygenated blood from the heart, bringing it to the lungs, oxygenating it, and then bringing it back to the heart.
Yes. To repeat that, what is the purpose of the pulmonary circuit? The purpose is to reoxygenate blood. You have deoxygenated blood in the heart, which came from the rest of the body. Bring it to the lungs, oxygenate it, bring it back to the heart, so now the heart can pump it to the rest of the body. I got it. Yeah.
How long does a full circuit take?
How long does it take? That's a great question. I have no idea. Pretty quick.
Like in 1 minute, it's circulate like 5.2 liter blood.
I'm sure it's on the second scale. I don't know. It's probably less than a minute, but I don't know how quick. I'm sure someone's figured it out.
I remember reading about that, two. It starts with the 2 and it's like really fast.
Really fast?
Yeah. Like less than half a second.
Oh, okay. Cool. Okay, so that's the pulmonary circuit. The systemic circuit is actually very complicated because it depends where we're talking. Like if we're talking about the right big toe or our left hand or the liver or the digestive system. But we can be very general. We can be very generic about the different locations of our systemic circuit. When we talk about the systemic circuit, we last left off in the left atrium. From the left atrium, we need to pump blood to the left ventricle. From the left ventricle, I'm getting a little cluttered here, but there's another large blood vessel right here. Called the aorta. So this large blood vessel delivers blood from the left ventricle out to the rest of the body. Makes a big loop. Branching off of the aorta at several points. There are 3 important ones up here. There's a bunch more down here. So branching off of the aorta at several points, which I can't draw all of them right now, those are systemic arteries. There are many different types of systemic arteries. Arteries that go to your spleen, arteries that go to your arms, arteries that go to your legs. We'll go over those specifically later. We're just going to call them systemic arteries for now. Systemic arteries branch into capillaries, systemic capillaries. This is where you get nutrient and gas exchange and waste exchange. You find systemic capillaries in every tissue of your body, whether it's your brain, again, everywhere. Capillaries branch back to veins. So here we have systemic veins. Systemic veins, they're veins from all over the body, they all converge into one of 2 large veins. The 2 largest veins are called the veni, the way to pronounce this is veni cavae. Veni cavae. There are 2 of them. There's one that comes from the top part of your body, your upper half, and there's one that comes from the bottom part of your body, lower half. If you had to guess the name of this top one, what's the name of this top? It's the superior vena cava and the inferior vena cava. You have 2 veni cavae, singular vena cava. I know it's a weird word. So there are 2. That's plural. There's a superior vena cava and an inferior vena cava that returns blood back to the right atrium. Yes?
What's the one above the left atrium that's going into, yeah, the one with the arrows coming out?
This one?
Yeah.
This is from the left ventricle out, so this is the aorta. All of this is aorta.
And that's from the left.
You got blood from the left ventricle going out of the heart to the aorta. So the aorta is an artery. The vena cava are veins. They're just the largest ones that either extend out from the heart or come back, bring blood back to the heart. You will be able to see this on cadaver hearts and the cadaver itself. They're very large. Yes?
So atriums receive blood and ventricles push blood out.
Yeah, that's a good way to put it. What's the difference between atria and ventricles? Atria receive blood from outside. Ventricles pump blood out. If you had to guess which ones are bigger, the atria or the ventricles, which ones have to be stronger? Ventricles, because they have to pump blood out of the heart. Atria just have to pump blood next door and down, so they can use gravity, so they don't have to be very strong. Which is stronger of the two, the right ventricle or the left ventricle?
The right.
Why left? Going to the whole body. Left ventricle pumps blood to the whole body, the head, the arms, the feet, everywhere. This has to be bigger. We will see that the left ventricle is very thick. It's the strongest part of your heart. It's noticeably bigger than the other chambers. So atria are smaller than the ventricles, and left ventricle is bigger than right ventricle. So, yeah, biggest, next big, both small. All right, that's our basic pathway. We'll get to more pathways coming up. Question?
Yeah, so when someone gets like a mechanical heart, does it work the exact same way?
You mean like a pacemaker? Or?
Yeah.
A pacemaker, what does a pacemaker do? We'll be talking about the electrical conduction through the heart, so hold that thought. It's more about timing the contractility of it. Some review. This hopefully sounds familiar. The heart is surrounded by serous membrane as well as a fibrous membrane. All right, if this is your heart, I'll redraw it here. This is your heart. Let me start actually closest to the heart, so I'm going to start on the bottom. The layer that immediately surrounds the heart that is not muscle, so the heart is mostly muscle. The layer that immediately surrounds the heart, that's the epicardium, also called the visceral pericardium. This is that inner layer of the serous membrane. Remember, serous membranes have two layers, the one against the organ and the one away from the organ. This is the visceral pericardium. You can also call it the epicardium. You've got the visceral layer, and then you also have the parietal layer, so that'll be the continuation of it, but facing away. And in between the two, that's where the serous fluid is, because we need lubrication as the heart's pumping. It's working all the time. We don't want it to have any friction. Right, and then outside of that, you've got a more protective layer. This is, the serous membrane is for lubrication. This outer layer, the fibrous pericardium, that's for like physical protection. So this is not serous membrane, this is a tougher connective tissue. Fibrous pericardium. So again, here's that visceral pericardium, or epicardium. What I have here in white, this is representing the muscle. Left ventricle is very thick. So this is the myocardium. It's the muscle part of the heart. So if you're referring to the muscle, that's myocardium. Like if you have a heart attack, a myocardial infarction, that means you're preventing blood flowing to the muscle of the heart, myocardium. And then endocardium is the innermost layer. So lining the chambers, that's endocardium. The endocardium, it's a mucous membrane. You can see it's this, what type, it's called endothelium. We're going to see endothelium in lots of places. What kind of epithelial tissue is this? Simple squamous. We have simple squamous with areolar tissue below it. That's endocardium. So you got endocardium facing the blood. You've got lots of muscle with nerves and blood vessels. Then you've got your serous membrane, your visceral and parietal, and then outside of that you've got fibrous pericardium. It's sandwiching and protecting all the muscle, making sure it's minimizing friction, and protecting the heart. Yes?
So the endocardium is both the endothelium plus the areolar tissue?
The endocardium is both.
The simple squamous.
Yeah. Endocardium is both endothelium and areolar tissue. The major, I don't want to listed endothelium because that's just a major feature. All right, so a lot of tissues protecting the heart because the heart's really important. But more about the muscle, the functionally interesting part of the heart, the myocardium. We've talked about these cells before. When we say cardiac cells, we're really referring to cardiac contractile cells. This is one type of myocardium. There's actually a couple types. Cardiac contractile cells, they are branched They are branched cells. They only have one nucleus. They are striated. So don't forget about those A bands and I bands and all that important stuff, because most everything that we talked about with how skeletal muscle works, also true about cardiac muscle. Most everything. Sliding filament theory, why would there are striations, A bands, I bands, all that stuff. It's all applicable here. Because they work all the time, they rely on constant supply of oxygen. So you need lots of mitochondria, you need lots of myoglobin, just like what type of skeletal muscle? What type of skeletal muscle has lots of myoglobin? Slow twitch. When I say it has an extensive circulatory supply, that means, going back to our diagram here, when blood is pumped out the left ventricle, it can go to the rest of the body, but the heart can also needs its own blood. The blood that's going through here isn't nourishing the heart. You need blood to go out of the heart and then go to these layers of the heart. So blood will be delivered to the myocardium after it gets pumped out. That's called the coronary supply. We'll learn about it later, but the heart has its own circulation. So that's what I mean by that. It has its own extensive circulatory supply. If you have a heart attack, that means you're blocking one of those arteries to the heart. What are these junctions between cardiac contractile cells called? These are called intercalated discs. And at the intercalated discs, we can find two important things. What do we find there?
Proteins.
We find proteins there. What proteins are they? Desmosomes and gap junctions. Desmosomes help transfer force. They're like a hitch. Oops. Desmosomes are like a hitch. They transfer force. Gap junctions help ions flow through. So here's a close-up of an intercalated disc. A gap junction will allow ions to pass through. So if you get ions to flow in one cell, it'll flow to the other cell also. So then if one contracts, the other's going to contract next, then the other one. It's going to be in rhythm. We want our heart to contract in rhythm. To contribute to that rhythm, we also want these desmosomes to link cells together so that if one shortens, the other one pulls with it.
I just wanted you to say that again.
Okay, yeah. Gap junctions. We need gap junctions so that if one cell is active, the other cell becomes active next. You're getting all this electricity to flow from one cell to the next, Yeah.
Gap junctions, are they found in the intercalated disc?
Gap junctions are found within the intercalated disc. So this whole thing is the intercalated disc. You find both gap junctions and desmosomes.
Okay.
Just the region, the border region. Take a moment. Raise your hand a few more times. Hands on three. 1, 2, 3. Three, say the letter. 1, 2, 3. B. B, yeah. Everything else they have in common. Excuse me. Everything else they have in common is just cardiac cells or branch smooth skeletal muscles. One really long cell. Okay, more about the heart in the next 5 minutes. We have the heart has a characteristic shape. And you can see that I'm just drawing those that basic way that we're all taught early on, but it still kind of has that shape. It's pointy on the bottom part and kind of bulgy on the top part. Anytime you have a pointy part of an organ, that's called an apex. It's a point, an apex. The top sounds weird, but the top is the base. So the superior portion is called the base. Usually you think of base as something more inferior, more on the bottom. But this is more, blood is going to come out of the base. This is where all the blood vessels are. There are no blood vessels on the apex. Can anyone think of a benefit of having blood vessels coming out of only the base and not the apex? What if we had blood vessels coming out of the apex?
They could flow down.
It would mostly flow downwards. If we had a blood vessel here, because of gravity, blood vessel would tend to only flow down. We don't want that. We want blood to circulate everywhere, especially the head, which is up. So we want blood to go up first, and then it can make its way down. It's in the mediastinum, and in its own cavity, the cardiac cavity. What else? Okay. And it's slightly to the left, just a little bit to the left. It's not perfectly so. What do you think this does to the shape of the lungs? Which lung is bigger? The right lung is bigger than the left lung. The left lung is smaller because it has to make room for the heart. And we'll see that when we get to the lungs. What also helps contribute to the efficiency of the heart is the arrangement of these cardiac contractile cells. They are arranged in a spiral shape. When you want to wring out a towel, for instance, you don't just squeeze, you wring it, right? By twisting it, you're getting every last drop out. You want your heart to be efficient. So the muscles are arranged in a circular spiral pattern so that it squeezes blood out of the heart. You want to be efficient, get oxygen to the lungs, get oxygen to the body, or get blood to the lungs, oxygen to the body. The ventricles squeeze from the apex to the base, in that order. We want to squeeze from bottom to top, from apex to base. We don't want to squeeze down, that's counterproductive. All the blood vessels are at the top. By having those gap junctions at the intercalated discs, that ensures that these are activated first, then these, then these, then these, and so on. As well as we'll go over the electrical path coming up. That's a good place to stop. Okay, so we'll continue this later. Monday, Wednesday, Live, I'll see you in 15 minutes. Tuesday, Thursday, I'll see you.